Hello guys, and welcome to my science tutorials. In today's video we want to continue the broader topic magnetic circuits, and we'll be looking at precisely magnetomotive force and magnetic field strength. Now in the previous video we looked at magnetic flux and magnetic flux density, but this time around we want to look at what magnetomotive force and magnetic field strength is. So let's begin by looking at what is magnetomotive force. Magnetomotive force. Okay, so by definition, magnetomotive force or MMF. Okay, so magnetomotive force or MMF. Okay, is the cause of the existence of a magnetic flux in a magnetic circuit. So the magnetomotive force is what causes the magnetic flux to exist in a magnetic circuit. So we say that this is the cause, or what causes magnetic flux to exist in a magnetic circuit. So this is the cause of the existence of a magnetic flux in a magnetic circuit. Okay, so mathematically magnetomotive force or MMF is given to us. Okay, so it's either MMF or FM depending on how you want to represent this. So it's MMF, so let me just use the MMF for the sake of simplicity. So magnetomotive force MMF is given to us by Ni, okay, and then the unit is in amperes. Okay, amperes or capital A. Now what do we mean by N? So the N is the number of conductors, or turns. Okay, that's the number of conductors or turns. And then the I is the current in amperes, Now because the N, which is the number of conductors or turns, doesn't have a unit, magnetomotive force also has the same unit as the current passing through the particular conductor. Okay, so this is the formula for magnetomotive force. All right, so the second one we want to look at is what we call the magnetic field strength. So magnetic field strength, or some people will say this is the magnetizing force. Okay, so by definition, magnetizing force is represented as H is equal to Ni on L. Okay, and then the unit is ampere per meter. Okay, now let's explain the terminologies over here. So the H, okay, is the magnetic field strength. This is the magnetic field strength, or the symbol for magnetic field strength. That is the symbol. Okay, and then the Ni, already we've seen it. The N is the number of turns, the I is the current, or basically the Ni over here is the magnetomotive force. Okay, we've looked at that already. And then the L over here, in this case, the L over here is what we call the mean length of the flux path, okay, the mean length. Okay, now let's make some deduction out of these two expressions. So let me use this color. So when we are saying that the magnetic field strength H is equal to Ni on L, or the magnetomotive force on L, if I cross multiply over here, I'm going to have the magnetic field strength multiplied by the length, or the mean length, is equal to Ni. Okay, remember this is just the number 1. Okay, so from here we know that Ni is equal to magnetomotive force, or Ni is equal to mmf. So in place of Ni, I'll use mmf. So it means that HL is equal to mmf, which basically means that my magnetomotive force is equal to the product of my magnetic field strength multiplied by the mean length of the magnetic flux. That is another formula for finding magnetomotive force. So it's either HL or Ni, the formula I gave over here. And also another formula that we need to take note of is this particular formula. The magnetic field strength H is equal to Ni on L. All right, so now that we have these three formulas in our brain, let's proceed to look at a couple of examples to appreciate what we are talking about as magnetomotive force and magnetic field strength. Okay, so the first example I have over here, I have a magnetizing force of 800 ampere per meter is applied to a circular magnetic circuit of mean diameter 30 centimeters by passing a current through a coil wound of the circuit. If the coil is uniformly wound around the circuit and has 750 turns, find the current in the coil. Okay, so this is the example that we have. So I'll write my solution. Okay, first of all, let me list all the parameters that I have. So I've been told that the magnetizing force or the magnetic field strength is 8,000 ampere per meter. So my H is equal to 8,000 ampere per meter. Okay, and then it's applied to a circular magnetic circuit of mean diameter. So the diameter, okay, is 30 centimeters, which if I convert to meters will become 0.3 meters. Okay, by passing a current through the circuit. So if the coil is uniformly wounded around the circuit and has, so my capital N, the number of turns is 750. Okay, I am to find the current I, which I do not know. All right, so let's proceed to look at the solution to this problem. Now remember, we said that the magnetizing force or the magnetic field strength H is given to us as Ni over L. Okay, Ni over L, and then we say the L is the mean length in this case. Okay, so now the problem is that the length, we do not know what the length is because we were just given the diameter. So to find the mean length is equal to d pi, or pi d. Okay, or another formula for the length is equal to, you know that the d diameter is 2 r, 2 times the radius pi. Okay, so you can say this is 2 pi r. So to find the length, the mean length in this case, you can either use 2 pi r or pi d. Okay, now since we've been given the diameter, okay, so we can just use that pi d and then we will find our answer. So already let's make our current the subject over here, so I will do the substitution very easily. So if I multiply the cross multiply over here, I will have HL is equal to Ni, and because I want the current I, I'll divide both sides by N, the number of turns. So I'll have my current to be equal to HL multiplied by N. So my current will be equal to, the H is 8,000, okay, and then the L, like I said, the L is pi d. Okay, so the d over here is 0.3, okay, and then I add the pi to it, all divided by the N, which is the number of turns. In this case, that is 750. Okay, so my current I is equal to, if I multiply 8,000 by 0.3 pi and I divide it by 750, I am going to get 10.05 amperes as my answer. So this is how we solve this particular problem, or a problem on magnetomotive force and magnetic field strength. Now it's also important that you know that the mean length is given by this formula. This is a very important formula when you are dealing with questions related to magnetomotive force and magnetic field strength. Very well, so let's proceed to look at another example. So I have a current of 5 ampere is passed through a 1010 coil wound on a circular magnetic circuit of radius 120 millimeters. To calculate A, the magnetomotive force, and B, the magnetic field strength. All right, so let's proceed to look at the answer for this particular problem. So I write down my solution. So the question is saying the current of 5 amperes, so my current is 5 amperes, is passed through a 1010 coil, so my N is 1000. Okay, and then the radius given to me is 120 millimeters, which if I convert, that will become 120 times 10 raised to the power minus 3 meters. Very good. So I am to calculate A, the magnetomotive force. Okay, the magnetomotive force, or MMF, which is the first thing I'm supposed to calculate, and then the B, I'm supposed to calculate the magnetic field strength, which is H. Okay, all right, so let's look at the option A. The magnetomotive force, like we said, it is equal to Ni. Okay, and then that will be equal to, over here we have the number of turns given to us, so that becomes very easy. We don't need to stress ourselves too much. So the magnetomotive force is equal to 1000, which is the number of turns, multiplied by the current, which is 5, and this will give us the answer of 5000 amperes as my magnetomotive force. All right, B, we have to find the magnetic field strength. So the magnetic field strength, as we know, is Ni over L, or the mean length. Now already we've calculated Ni, which is the magnetomotive force, so I can say that this H is equal to mmf over L. Are you okay? Another way, because the Ni, we've already found it to be 5000. Now the problem here is that we were given radius, and then to find the mean length, we know that the mean length is equal to 2 pi r. So this whole formula is equal to magnetomotive force over the mean length, which in this case is 2 pi r. So that is what we are going to use. So my magnetic field strength is equal to, already my mmf I've calculated is, that is 5000. Okay, or you can just use 1000 multiplied by 5 all over 2 pi multiplied by the radius, which is 120 times 10 raised to the power minus 3. Okay, so if I compute all this into my calculator, 5000 divided by 2 pi multiplied by 120 times 10 raised to the power minus 3 will give me the value 6631 ampere per meter as my answer for this particular problem. So thank you so much for watching. This is how we solve problems on magnetomotive force and magnetic field strength. So it is important to note that as we said, this is the formula for magnetomotive force, which is Ni. The N is the number of conductors or turns, and then the I is the current. Also, the magnetic field strength H is equal to Ni on L, where the Ni is the magnetomotive force, and then the L is the mean length. And it is also important to know that the mean length is equal to either 2 pi r or d pi, or pi d. That is the formula, as we can see over here. And once we know those two formulas, it is easy for us to solve our problem. So thank you once again, and I'll see you in the next video, where I'll be attempting the solutions to the homework that I gave you on magnetic flux and magnetic flux density. So thank you once again, and bye bye.